student. Today we are going to learn about successive approximation analog to digital converter. So let's start with the topic successive approximation analog to digital converter. This technique is the most commonly used technique that is useful for general purpose application. In this technique, the conversion time is maintained constant and it is proportional to the number of bits in the digital output. This technique is advanced version of digital RAM type ADC. However, it has a more complex circuitry than the digital RAM AD converter, but it takes a much smaller conversion time. Here the conversion time is not dependent on the values of analog input. So in successive approximation ADC, the normal counter is replaced with the successive approximation register, and that counter is known as SAR. This register counts by changing the bits from MSB to LSB according to the input. This type of ADC is commonly used in data acquisition applications and it performs very high speed operations. So now this is the working principle of successive approximation type ADC. In this ADC, the circuit employs a SAR, that is successive approximation register, which finds the required value of each successive bit by trial and error method. So here this SAR is used here, the trial and error method. The output of SAR is fed to the D/A converter that converts the digital to analog. This is the digital to analog converter. The output of digital to analog converter is applied to the non-inverting input terminal of the comparator, and the non-inverting inverting terminal of comparator is connected to the unknown input voltage Vin under conversion. Now the comparator output is used to activate the successive approximation logic of SAR. So this is the basic working principle, and as you can see here in this diagram, this is the comparator and these are the terminals. This is non-inverting terminal and this is inverting terminal, and this is the Vin voltage that is applied to the inverting terminal. And then this is the SAR. When now the start command is applied here, the successive approximation register produces the binary bits. These are B1, B2 up to n bit, and then that bits is applied to the D/A converter. Here this is the end of conversion. This is the clock pulse. Now the output of this D/A converter is again applied to the comparator. So this is at the non-inverting terminal of the comparator. So here there are two conditions. This type of ADC operates by successively dividing the voltage range by half. When the start command is applied, the SAR sets the MSB to 1 while the remaining bit sets as 0. So if we take an example of 3-bit A/D counter, the trial code is initially 100. The output of SAR is converted into analog equivalent reference voltage VR and gets compared with Vin. So here there is two conditions. Condition number 1, when Vin is greater than VR, and condition number 2 is when Vin is less than VR. So here if the Vin is greater than VR, then the trial code 100 is less than the correct digital value, means the MSB retained as 1 and the next significant bit is set to 1. Therefore the trial code will becomes 110, means this 100 here the MSB retained as 1, so this is retained as 1, and the next bit, this is the next bit, is set to 1. So now this bit is set to 1 and the remaining is 0. So the sequence is repeated, and in the condition number 2, when Vin is less than VR, the trial code 110 is greater than the exact digital equivalent. Therefore, the comparator reset the second MSB to 0 and proceed to the next most significant bit. This process is repeated for all the remaining lower bits in sequence until all the bits positions are tested. So here finally the end of convergence signal is sent out when all the bits are scanned and the value of D by A converter output just crosses V in. So this is the basic operation, and now we will see here this is the start bit. This is B1, B2, B3 and these are 0, 0, 0. And now initially when the start command is applied, then this is set as 100, so the trial code will be 100. Now because there are two conditions, when V in is greater than VD and V in is less than VD. So if V in is greater than VD, then this 100 will become, because MSB first MSB is set written as 1, so the this is 1, the MSB is written as 1 and the next bit is 0. So this is the first step. And in this this is the second condition. When V in is less than VD means it resets your previously bit, means the previously bit is 1, so it reset here and this is 0 and it will set to the next bit. So this one will be set to next. So this is previously set bit is 1 and then it is reset here and it will set to next, that is 1 and this is 0. So this process is repeated here. Now again this 110, this is the trial code, and this is again there are two conditions. When V in is greater than VD means this is the MSB is written as 1, so the MSB is written as 1 and it will the next bit is set to 1. So this is 1 1, so MSB written as 1 and set to the next bit, so this is the 1. And now when V in is less than VD, so this is the second condition, and here it will reset your previously bit. So here is the previously bit is 1, so it reset and this is 0, so it will reset the previously bit, means 1 is here, like this is 0, and then it will set to next. So this one will set to next, so this is 1, so this will becomes 101. Now here when V in is less, again this is there is two conditions, 0 1 0, so this is V in is greater than VD, so this is 0 1 1, and V in is less than VD, so this is 0 0 1. Why this is here? Because again the condition is repeated, and V in is greater than VD means the MSB written as 1, so this MSB is written as 1 and next bit is set to 1, so the next bit is set to 1. So this is the condition, and when V in is less than VD, then it will reset your previously set bit. So the previously bit is this, so it will reset here, so this it will become 0 and it will set to the next bit, so this is it will become 1. So now again the process is repeated here. Again this 111, here there is two conditions, V in is greater than VD and V in is less than VD. So here when V in is greater than VD means there is no set bit here, no next bit is here, so this will become as 111. And here when V in is less than VD, so it will reset your previously bit, so the previously bit is 1 here, so it will reset here and no next bit is here, so this will become 110. Now this is the next code 101. So again there is two conditions, Vin is greater than Vd. So here this is the MSB is written as 1 here. So this is the last bit remained as 1. So there is no next bit. So this is again we will apply the same bit. So this is 101, and when Vin is less than Vd, then it will becomes 100. Why it will becomes 100? Because the last bit is reset here. So this is 100 and there is no next bit, so it will become 100. And again 011, here again there is two conditions, when Vin is greater than Vd like this and Vin is less than Vd like this. So here when Vin is greater than Vd means again MSB is written as 1. So MSB written as 1 and there is no next bit. So we will write here again the same bit here. So this is the same here 011, and again the second one condition is here when Vin is less than Vd. So this is 010. Why? Because the last bit is reset here and there is no next bit, so it will become 010. This is the last bit here 001, and again here are two conditions, when Vin is greater than Vd. So here the MSB bit is 1, so there is no next bit is here. So this will become again same here. So this is 001, and in when Vin is less than Vd, so again the last bit is reset here. So this is 00 and there is no next bit. So this is the process for the 3-bit ADC, and for up to it is used up to n-bit ADC. So we will consider here this is the 3-bit A by D converter. We have already explained these conditions in that diagram, and this is the basic logic diagram of SAR type A by D converter. This is the output, and the advantages and disadvantages of A by ADC. The advantages of successive approximation type ADC is the conversion time is equal to the n clock cycle period for an n-bit ADC, thus conversion time is very small. The second one is conversion time is constant and independent of the amplitude of the analog signal. And similarly this technique has some disadvantages. These are like it has more complex circuitry than the digital ramp A by D converter, and the conversion time is more compared to flash type ADC. So these are the advantages and disadvantages of the successive approximation type ADC. Thank you for watching.